In this video, we are going to create a few ionic compound Lewis structures. So for our class, I only ask you to learn how to draw binary ionic compound Lewis structures. So Lewis structures made of two types of atoms. In order to do this, you will definitely need your periodic table, which will contain the number of valence electrons, the element symbols of everything that we're going to be going through. So our first example is sodium sulfide, right? We know it's binary because it's one element that's a metal and one element, sulf, standing for sulfur, that's a nonmetal. The first unofficial step of creating Lewis structures is to figure out what the formula is, because you need to know how many of each element you have. So sodium has the element symbol of Na. Sulfur, which is the nonmetal that we're working with here, sulf standing for sulfur, has the symbol S. Sodium has a +1 charge, sulfur has a -2 charge. We need these things to come together in a way that creates a neutral compound. So in order to balance these out to have a neutral compound, I would need 2 sodiums for every 1 sulfur. So my formula will be Na2S. This is important because the first step of drawing a Lewis structure is to write out the element symbol for every atom involved in the compound. So I'm going to have 2 sodiums and 1 sulfur. So now that we have the element symbols out, step 2 will be to draw the electron dot diagrams. So you'll use your periodic table and you're looking for the number of valence electrons, not the charge, valence electrons. Sodium is group 1, so it has 1 valence electron. Sulfur is group 16, so it has 1, 2, 3, 4, 5, 6 valence electrons. I am setting this up in a way that will make my transferring as easy as possible. Doesn't matter really where you put the electrons, as long as you don't double dot before every side has an electron. Now, we have to be careful here, because when we work with ionic compounds, we are talking about the stealing of electrons. So this differs from our covalent Lewis structures, because what we're going to do is we are going to draw an arrow that shows the actual transfer of this electron. So this sulfur will pick up this sodium's electron here. And then this sodium will also transfer an electron to the sulfur as well. So this is combining the first 2 steps. So step 1 is drawing the electron dot diagrams. Step 2 is showing the transfer. So an arrow implies the transfer of electrons. The final step is to clean it up. Now, when we clean it up this time, compared to what we've done with covalent compounds, it's a little bit different. So you have 2 different options of writing out this final structure. You can do this, where you write out the element symbols again, Na, Na, and S. Now, each of my sodiums have lost 1 electron, so you have to include the charge. And we'll talk about why that's important in just a minute. Now, sulfur has gained 2 electrons. So what I like to do is I like to color code these just so you can see where those electrons ended up. So I'm going to make the stolen electrons red, so I can see that sulfur has picked up those additional electrons. Now, we want to hold in all of my anions electrons, so we use brackets here. Because sulfur picked up 2 new electrons, it will have a -2 charge. It's very important to include the charges, because that's what holds this whole thing together. So it's the opposite charges attracting, these attracting with this. Those opposite charges are what holds my ionic compound together. Now, this is different from what we learned in covalent compounds. I'm going to give you an example of a covalent compound here. For example, the finished Lewis structure of water, a covalent compound, might look something like this, where my lines indicate shared electrons. These shared electrons are what held my covalent compound together. So lines on covalent compounds imply shared electrons. That's what holds it together. But for ionic compounds, it's the charges that hold it together. So if you don't write the charges, you don't have a compound because you're not telling me that anything is holding those together. So be careful. Now, I said there's a second way that you could write this. So if you wanted to, what you could do is say, okay, well, I have two sodiums here. I can write a coefficient 2 Na plus, and then do your anion afterwards in the same way. So still brackets, still charges. So if you put the coefficient in front, you're telling me you have two of these +1 charges, which will create an ionic compound with this -2 charge. So there's two different options here. Option number 1 is correct. Option number 2 is correct, as long as you have the charges, because that's what holds them together. And you do not have lines, because lines imply shared electrons. So we're going to do one more example here. In our next example, we will be looking at aluminum oxide. So again, we need to start by figuring out how many of each we have. So the element symbol for aluminum is Al, and it has a 3+ charge. The element symbol for oxygen is O, and it has a 2- charge. I think I'll do the crisscross rule for this one. So I'll take the 3 from the metal, give it to the non-metal. I'll take the 2 from the non-metal, give it to the metal. So my final formula for aluminum oxide is Al2O3. So now I can start with my electron dot diagram. So I'm going to need 2 aluminums and 3 oxygens. I'm going to move that down just a bit. Now the electron dot diagrams, aluminum is a group 13 metal, so it will have 3 valence electrons. Both of them will have 3 valence electrons. Oxygen is a group 16 nonmetal. It will have 6 valence electrons. All right, so electron dot diagrams have been set up. Now we show the transfer from the metal to the nonmetal. Remember, metals have very low ionization energy, so are bad at hanging on to their electrons. Nonmetals have great electronegativities, so very large electronegativities, so they're good at stealing electrons. These oxygens each need 2 more electrons. So I will give this electron arbitrarily to this oxygen, and I'll move this one here, and then I'll move this one here. Arrows implying complete transfer, not sharing. Here, here, and here. Now at the end of the day, every electron in your metals should be transferred. Every nonmetal should have a full octet. So if something goes wrong and you are left with extra electrons in your metals, or you have missing electrons in your nonmetal octets, that means this formula was not correct. And you should go back and double check that, which is why it's important to do this as a preliminary step. So now we have our electron dot diagrams. We've showed the transfer of these electrons. We are ready to clean this up. Again, I'm going to show you 2 different ways to write this. You'll see why one way might be a little bit more advantageous. So I can start by writing each of our symbols again. So 2 aluminums, 3 oxygens. Now each aluminum gave up 3 electrons, so I just put a +3 charge next to both aluminum. Here's where it gets kind of annoying if you do it this way, because now I have to draw 8 electrons around each of these oxygens. Typically I would color code the shared electrons, but in the interest of time, I'm just going to go ahead and add those. So brackets to hold in all your new electrons. Each of these oxygens, I'll do one of them, gained 2 electrons. So I'm just going to color over. That will give me a 2- charge. So same thing with the next oxygen. We have to do 1, 2, 3, 4, 5, 6. I guess I've decided to go ahead and color code anyways. So here's my first gained electron. Here's my second gained electron. That is a very sloppy Lewis structure. Please do better than I do. Now this oxygen also gained 2 electrons, so it'll have a charge of -2. And then our final oxygen, here are my original electrons. And then we'll add in the electrons it gained. And we put brackets around it to hold in all its new electrons. And again, it gained 2, so it'll have -2 charge. So again, this is the first method that you can use as long as you have a neutral compound. So I have to include my charges. So +3 + 3, 3 - 2s, those are what hold my compound together. Now, my preferred method, and you can use whichever method you'd like, is to do the shorthand version. So I have 2 aluminums. So I'm going to write a coefficient 2, not a subscript, 2Al3+, and I've got 3 oxygens, so coefficient 3, and then I can make this a little bit more simplified here. And again, my oxygens have a 2-. So you have 2 options. These are not part of my Lewis structure. So option number 1 is to individually write out each element symbol, and that's fine. Or option 2 makes it a little bit more clear or simple as just writing out one of each symbol, but then including coefficients to tell me how many of each I have.